In this lab, we observed off-axis aberrations, namely coma and astigmatism. Coma is an off-axis aberration which occurs when the magnification of an optical system varies with pupil position and field height. Coma cannot be detected on axis as it is characterized by the focus of tangential and sagittal rays. These focus at differing heights unless the field value is 0, meaning we are on axis. Here are the wavefront error and ray error equations which characterize coma. As it can be seen, there is a linear dependence on the field height and quadratic dependence on the pupil coordinate. If we create an off-axis field, meaning h has a particular value, and find the deviation epsilon y from the axial center at which the optical system retrieves a ray at the pupil maximum, i.e. y sub p equals 1, then we can quantify the coma present in the system. This is precisely what we did in lab using a mask lens microscope combination, similar to last week. Astigmatism is another off-axis aberration that occurs when the tangential and sagittal rays focus at different longitudinal distances. In this diagram, we see there is a focal line which exists for the tangential image and also for the sagittal image. The tangential focus exists where the tangential rays intersect, and the sagittal focus exists where the sagittal rays intersect. These are the wavefront error and ray error equations for astigmatism. Note that unlike coma, astigmatism has a quadratic dependence on the field height. To find astigmatism, one may find the best focus position of the sagittal and tangential rays and record longitudinal and transverse deviation with an imaging system. This is exactly what we did in lab using a microscope. Unlike last lab, we aren't scanning across an entire pupil to make ray fan plots showing the ray error versus pupil coordinates. Instead, we are showing the relationship between the ray error and the off-axis field values. So, for differing values of h, we are adjusting our microscope translation off its initial centered values to focus onto an image and find the corresponding ray error.
Combining the knowledge from previous labs, we first aligned the laser beam with the optical rail. We then added the fold mirror to rotate the light by 90 degrees. We aligned the microscope and the 50 micron spatula filter to make the beam expander. We ensured that everything was properly aligned using the shear plate. Finally, we placed the test lens and the Harlan mask. From there, we aligned the microscope with the Harlan mask by finding the image of the mask and focusing on the microscope. Locking down the rail, we then moved the microscope using the lateral and longitudinal translation stages to make the original focus position. To create the off-axis field, we then moved both the lateral and longitudinal translation stages by 5 millimeters. To measure coma, we want to look at each of the 4 pinholes, top, bottom, left, and right, individually. We then use the lateral translation stage to adjust the position of the lens and mask. Once we center the individual pinholes, we can then read the measurement. Taking the measurements from all 4 pinholes, we can then find the amount of coma. Measuring the astigmatism is done in a similar manner. We block off the top and bottom, or the left and right pinholes, to take measurements rather than each individual pinholes. We want to change the longitudinal as well as so to adjust the crosshairs. Longitudinal displacement will allow us to amount of astigmatism, W222, while the lateral values will be the overall astigmatism. Finally, to confirm the results, we want to find the coma and astigmatism at different fields. The lab calls for us to measure the 2 aberrations at the fields -5, -3.5, 3.5, and 5, but due to time constraints, we will only be measuring 3.5 and 5 fields.
After collecting data, we were able to plot the results. We plotted field height versus epsilon y. Epsilon y is the y-direction translation of the microscope that was required to refocus the beam of light onto the crosshairs located at the end of the table. We plotted the results first for coma. The sagittal plots use epsilon y values from the edges of the y-plane of the mask, and the tangential plots use the epsilon y values from the edges of the x-plane of the mask. Here you can see that a linear relationship was found between the field height and the change in y. Next, the tangential and sagittal astigmatism results were plotted. We expected to see a quadratic relationship between epsilon y and field height, however, a more linear relationship was found. Perhaps if we had more time to collect data at more field heights, we would have been able to see a quadratic relationship. Additionally, we were able to calculate the amount of astigmatism present in the system by using the z-values we measured in lab, the field height, the focal length of the lens, and the diameter of the beam. This value is 310 microns for h equals 5 and 160 microns for h equals 3.5. Using our measured epsilon y values, the field height, the focal length of the lens, and the diameter of the beam, we are able to calculate the amount of coma present in the system. For h equals 5, W131 is 68.59 microns, and for h equals 3.5, W131 is 61.5 microns.